All right, good. We're going to test our knowledge of this now. Okay, let's see. I'm not going to ask you to do the versions that we did, use Excel to do this. Those of you that want to use R, you can use R for this, or other Strata or other software. But I think for most of us, we're going to have the easiest time using SPSS. So let me see, where did I put this folder? I gotta clear things out here so I can see. Here we go. Okay, problem one. Now I'm gonna open it. Well, first of all, I'm gonna open a document that goes with this. Okay, this is a document I uploaded for okay, let me try and close this. This is a homework document that I uploaded. Okay, now this is versus 3 different problems here. Okay, problem number 1. The data in the file TC by education.sav, that's total cholesterol by education, saved in 3 forms. It's saved as an Excel file. It's saved as a comma delimited file. If you're using R, you're going to use that to import the data. And it's saved as an SAV file, an SPSS data file. Okay, so I'm going to open up that data file in a moment. But first, I'm going to read the rest of this. Represents the total cholesterol level measured in men aged 50 to 54. Data is organized into 3 values for levels of education. 1 represents graduated high school, 2 represents some college, and 3 represents college. Okay, and what we're examining here is the mean cholesterol level in these 3 populations. And the populations, not the samples, but the populations, are they equal? Okay, so we're going to open that. We're going to open that file, but first we're going to ask ourselves, what's the null and alternative hypothesis here? What's our null hypothesis going to be? Right? It's going to be that the mean of these 3 groups are equal, right? Okay, what's the alternative hypothesis? That there's at least 2 groups that are the means are not equal. Okay, we're going to take a look. We're going to calculate descriptive statistics in box plots just so we can examine the data. I think we should add to that also create a histogram. And when we create the histogram, let's examine it and take a look to see whether or not it's symmetrical. Okay, and then what are we going to do? We're going to perform an analysis of variance. Okay, using our preferred method, which is SPSS, because it's way less work, right? We're going to check the p-value, right? Decide whether or not we can go on to our next step, which is produce our post hoc tests. Okay, you reject the null hypothesis. If you do, you can go ahead and do your post hoc tests. Okay, let's do Bone-Ferroni this time. And we're going to decide if there is a statistical difference in average cholesterol levels based on level of education, we're going to try and decide where it is. Are men who graduated college versus men who completed high school? Is that where the difference is, and so on and so forth? Okay, so I'm going to let you guys open that up and give that a try. And we'll work on that. I'm going to give you some time, 5 or 10 minutes to work on it. And then we'll go back and do it together. What's that?
The file, we can't find the file.
It should be on. It's under lab. I'm sorry. You can't find the assignment. It's under assignments. I'm sorry. This is under assignments. It won't be in the lab section. It'll be under assignments. It's 5B because I haven't created the thing where you can just put in little answers and get your feedback right away yet. But you have the actual document and data files there.
So which file is it?
It's TC by education.sav because you want to do it using SPSS. Okay, and again, do your descriptive statistics first. Do a histogram, do a box plot, calculate the means, and so on. I'm sorry, say again?
Can you just go to the modified document? The Word document.
Oh, the Word document, okay. You guys working on it at home there? I hope. Okay. It's TC by Educate. It's document is called PH751 Fall 2014 Homework 5, HW5. If I turn that on. Okay, you guys are doing it with SPSS at home, right? Not Excel, right? And if anybody at home has a question and they want to talk, I'll turn on your microphone and we'll experiment and give that a try, see if we can hear you. Anybody want their microphone turned on? No one? No volunteers. Must be a question or two, right? Okay, if you're shy, you don't want your microphone turned on. If you have any question, type it into the chat box. They're fairly normally distributed, right? Not too horrible. So this isn't that hard, right? I mean, this is a pretty valuable tool. You can have a lot of data, a lot of different groups, like say ethnicity. Let's say you're comparing different ethnic groups, or different boroughs, or different professions, or multiple exposure groups, right? You can have a lot of different groups, and you can analyze the data to look at for differences between means in all of these different groups, right? All in one fell swoop here, very quickly. Right, and it's using SPSS. It's a pretty simple test to implement. Now, what kind of data are we working with here? We're working with how many variables? Right, how many variables are we working with here? We're working with multiple groups, but the number of variables, 2 variables, right? One variable is the groups, right? Variable is one variable. If you look in SPSS and you look at the number of columns that we're dealing with here, it's only 2. One variable is the group. It could be high school graduates, could be some college, could be college graduates. There are 3 values, A, B, C, 1, 2, 3, within that variable. Okay, the other variable is an actual measurement, cholesterol level, right? What kind of variable is that? That's a numeric variable. So we're dealing with a categorical variable, right? Categories. And we're dealing with numerical variables. So we have a combination of a categorical variable and a numerical variable. So when we want to do an analysis of that kind of data, we have two great tools. If our a categorical variable has only two values, right, male or female, for instance, right, then we can use a t-test. If our categorical variable has more than two values, then we can use analysis of variance to detect whether there is a statistical difference between the means and in those groups, right? So that's one situation we might run into. We're going to go over this, and at the tail end of tonight, I'm going to talk to you about other situations where you have different kinds of data. For instance, how about when you have two variables and it's numerical data? So let's say for instance that you have, let's see, uh, uh, population growth, annual population, and CO2 levels for that year, right? For each year, you have a value for each one of them. You have a numerical variable for the population. You have a numerical variable for CO2 levels, or maybe CO2 production, let's say. And you want to see if there's a relationship between population and CO2 production, for instance. Well, we have numerical variables in both places there. There's not going to be any means involved. So we need a tool for working with two sets of numerical variables when we want to show there's a relationship. Say, as population goes up in a country, the CO2 production goes up also. Okay, well, how about another situation where you have two kinds of categorical data? For instance, let's say drug use and HIV. You have data where you've collected it for a number of individuals you randomly sampled, and you ask them if they've used intravenous drugs, and you check their HIV status. So what do you have now? For each individual, you have a yes or a no, a 1 or a 0, or 1 or a 2, for drug use and for HIV. What kind of two variables we have there? We have HIV status, we have intravenous drug use, we have categorical variables, two of them. So how do we demonstrate that there's a relationship between drug use, intravenous drug use, and HIV? Well, now we got to deal with the situation where we have categorical variables. So we have situations where we have numerical and categorical variables, and we have two categories, numerical and categorical variables, and we have more than two variables in the categories, numerical and numerical, and categorical and categorical. So we're running through all these different possibilities. Well, why is this important? The reason why this is important is as you start to apply this stuff and you start working on your projects, for instance, this semester, you may find some interesting data that involves numerical and numerical data. And you want to show an association. Anybody know what association would be called when you talk about numerical and numerical? Right? What would we call that? That there's an association between as one thing goes up, another thing goes down, or as one thing goes up, another thing goes down. What was that? Correlation. Exactly. You're going to attempt to find out whether there is a correlation between those two sets of numbers, right? And you may want to do this. So next week and the week after, we're going to be dealing with statistics that deal with these other kinds of variables. So I want you to keep in mind as you start to think about what to use, what kind of project to do, because the kind of test that you're going to apply is going to depend on the type of data that you're analyzing. Is it numerical and numerical? Is it categorical and numerical? Is it categorical and categorical? And you're going to, like this last 3 weeks of the semester, you're going to be exposed to the tools up to now, whatever first 10 or 11 weeks we've had, you've been learning the basics. These last 3 weeks, like now with analysis, t-test, analysis of variance, correlation, regression, chi-square, odds ratio, which we're going to do in the coming weeks. Those are your actual toolbox that you're going to be using in the future to do analyses and stuff like that to try and deal with data. So let's give this a try. I'm going to go. I think you guys have had a chance to do this. Let's try this one together. Okay, so you guys are home or still there, I hope. And okay, I'm going to open up SPSS. Have my data set, and you can see that. First of all, number one, you see my the column here is education. That's my categorical variable, and total cholesterol is a numerical variable. It's an actual blood test or number associated with each subject. Each one of these rows represents a subject. If I go into the variable view, in the variable view, the first row represents the first column. Okay, and it's shorthand. In shorthand, it's called EDUC, education. Okay, you can actually change. I'm going to label this a little bit better. I'm going to call it level of education. And by typing into this box that says label, it's going to, when it creates a graph or a table, it's going to give it a more descriptive label, make it more useful for me when I cut and paste it into a report or a project or something like that. Well, if you have a nominal or categorical data, right, this is nominal. If you have that kind of data, you can actually identify what the values represent. So in this case, we've already coded it so that 1 represents graduated high school, 2 represents some college, 3 represents graduated college. My second column represents the value T cholesterol, or total cholesterol. I'm going to actually go in there and edit that again to say total instead of T cholesterol. Under the label, even though now SPSS has strict requirements on the variable name, this education and T cholesterol. Can't have any spaces, can't begin with a number, it's got to begin with a letter, can have numbers and letters, can't have special characters, can't have spaces and so on and so forth. So it's not really convenient to make a nice chart or table or something like that. But you can use a label to substitute for that variable name when SPSS actually applies it. So I'm going to change this to total cholesterol instead of T cholesterol. And you'll see that when we create the tables, we're going to get those names right there. So the second row represents the second column or the actual numerical variable. SPSS calls it a scalar variable or scale. Okay, so I'm going to go back to the data view, and you'll notice that you can see the first person graduated high school, what the cholesterol level is, and so on and so forth. If I want, I can go up here to view, and I can turn on and off the value labels. So this actually shows the data that's been entered, which is 1s and 2s. If I want to get that back again, I can go to view and turn on value labels again if I want to see the actual substitution for those numbers. And where to get that term graduated high school? It got it from our coding in the variable view. If I had changed it to, recent graduate or something like that, that's what you would see there for the number 1. Okay, so now let's go ahead and do some of our tests. First thing I'm going to do, I'm going to say analyze, descriptive statistics, explore, because that's going to give me the most information. I'm going to move my numerical variable into my dependence list. My numerical variable is what? Total cholesterol. And I'm going to move my categorical variable, nominal variable, categorical variable, into the factors list. Factors list meaning the groups that I want to break it up into. Statistics, descriptives, 95% confidence interval, fine, that looks good to me. How about plots? Well, plots, we know it's going to create a box plot automatically, right? Side-by-side box plots. I'm going to ask it to do histograms as well. We haven't talked about normality plot tests yet, so I'm going to leave that unchecked. I'm just going to do a visual analysis of whether or not it looks like these groups are normally distributed. I'm going to click continue, and I'm going to click OK. And notice I have display both the statistics and the plots. Okay, SPSS opens a whole new window, our output window, and you can see just as before, it processes these cases, and it says, okay, within the group graduated high school, we have 44 individuals. Some college, 27. College graduates, 65, and so on and so forth. And the mean cholesterol for high school graduates is 203. For some colleges, 206. And for graduated college is 183. Okay, I don't know about you, but when I was in college as an undergraduate, I ate a lot of pizza. I'm sure when I graduated, my total cholesterol was horrible. So I think in real life, it might go the other direction. So trust me, One thing you don't learn how to, maybe that you people are nutritionists, you public health people. I went to a engineering school as an undergraduate, and trust me, we didn't eat well. Okay, so at any rate, how about our histograms? Let's take a look at them. They look roughly normal, don't they? They look symmetrical, fairly symmetrical. That they're the mean. They look bell-shaped and so on and so forth. They're not gigantic samples, so I wouldn't expect them to look completely normal. There are tests that we can do for normality. We're not up to that point yet at this point. So now the question now is the mean for group 1 and group 2 and group 3 all equal to one another, our null hypothesis? Or is at least two of these means not equal to each other? Mu1 is equal to mu2 equals mu3, or alternative hypothesis that at least two of these means are different. Okay, so now let's take a look at our results. Stem and leaf plots, same thing as the box plots, really. Well, look at our box plots. Right? Variability doesn't suggest it's going to be very easy to demonstrate that, does it? Now, we got decent sized samples here. I can see a number of outliers and stuff like that. I'm not going to worry about that at this stage. So, looking at the box plot, looks kind of hard to tell whether or not we can really distinguish between these. The means are different, particularly, I think this one and this one, some college and graduated college. Maybe not. Maybe this is more. Nope, that's closer. Well, let's see what we get when we run our analysis of variance. I'm going to go up to Analyze, Compare Means. I'm going to go to One-Way Analysis of Variance. I'm going to move into my dependence list again, the numerical variable, total cholesterol, into my factor list, level of education, and I'm going to click OK. Okay, let's see what our F value comes out to be. Our F value comes out to be, whoa, surprise, there was enough data there for us to determine that there's a difference between at least two of these means. Well, let's take a look at this. Between the sum of squares between groups is 15,148. Well, what is that? That's the sum of squares between the three means, right? Divided by the degrees of freedom is three groups, so it's 2, just as we did before. 2 into the 15,000 is 7,500, right? And within the groups, all of the individual values within each group and the mean of that group, all added together, squared and all added together, all those differences divided by the degrees of freedom. What's the sample size? How many individuals do you think were here? If the degrees of freedom were 133, how many people did we have? N1 plus N2 plus N3 minus 3, it must have been 136, right? So it's 133. So 133 into 175,000 is 1,317. Our F value is the mean square between the groups, between the means, in other words, and within the groups, divided by within the groups, 7,500 divided by 1,300, F score of 5. And we know from our table that we looked at before that if you have two groups, right, three groups, 2 degrees of freedom in the column, and this is a much larger sample. You have to go, remember we went all the way down to 120 at the bottom, that our critical value is going to be under 3.89. It was 3.89 when it was only 15 people. Now it's 136 people, right? So our critical value is going to be even smaller than 3.89. So we know 5.79 is going to 49 is going to be pretty certainly going to be something that's going to let us reject our null hypothesis. SPSS, in fact, tells us what our probability of being wrong if we reject the null hypothesis of a type 1 error. And that's equal to 0.04. And what's our tolerance for it again? 0.05. So since our probability of making a type 1 error if we reject the null hypothesis is less than 0.05, we go ahead and reject it. And we accept the alternative that there's a difference. Which ones? I'm sorry, yes.
Earlier we had selected a different alpha, we'd be in a different situation, right?
Yes.
199.
Yeah, well, we see it right here. If we had said 199, it would have been 0.01, right? Okay, our alpha would be 0.01. Would we reject the null hypothesis? Take another look. What's the significance? We would still reject it. The first example that we did, we wouldn't have, because it was 0.046 or something like that. It just barely made it. So if our alpha had been 0.01, we would have failed to reject. But this one, the significance, the p-value is so small. SPSS tricks us by using significance for the p-value. The p-value is so small, our chance of being wrong or making a type 1 error, if we reject, is less than 0.01 even, right? So we would still reject the null hypothesis, right? Okay, so now, what do we do now to figure out which ones of these are different, right? Well, we go and do our post hoc test. So I'm going to go to analyze, compare means, one-way analysis of variance. Now, conveniently, SPSS doesn't make any changes if you go back and redo this. So all our options we chose before are still there. I'm going to go into post hoc. I'm going to do Bonferroni. I'm going to click continue, and we're going to get exactly the same tables, except this time we're going to get that 2x2 table with all the different permutations. And let's see what we got. Graduated high school versus some college. Oh, that's not very significant. Graduated high school versus graduated college. Aha, look at that. That's significant. That's less than 0.05. So we can say that there's a difference in the average total cholesterol for people who graduated, population of people who graduated high school versus graduated college. Okay, how about some college versus graduated high school? Now, how about some college versus graduated college? Yes, we have another one of these two groups that is statistically significantly different. Some college versus graduated college. And this last one's just repeating the ones we've already seen. Graduated college, graduate versus graduated high school, we know that's significant. And graduated college versus some college. The only one that we couldn't demonstrate a difference in was graduated high school versus some college. Let's go back and take a look at that. Graduated high school versus, well, look at this. The means are close together, and the variability, it doesn't look like this is all captured within this variability and so on and so forth. We're able to tell these two were different. We're able to tell these two were different, but we couldn't really demonstrate that these two were different. Okay, so that's where we stand, right? I mean, that's what we were able to do here. So, any questions? Right?
So I know we're not there yet with the normality tests. And
Yeah.
Professor Waldron had explained in lecture why it wasn't always a good idea, but just looking at the data, it's clear that there are outliers.
Yeah, that's another thing. I think in your list of assumptions, you assume that there were no outliers within the data, and wasn't that in your list of assumptions? No, you don't remember
You
that?
assumed that it was normal.
Yeah. 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 Okay.
I'm kind of just wondering how that, I guess maybe it's not an appropriate question since we're not at normality tests. But,
Are we going to do normality tests? Maybe next week?
I don't
No?
like normality tests.
Okay. Just examine the normal distribution and make a judgment for now.
We might, during the regression, cover two residuals plots.
Okay. Yep.
But I think usually normality is better assessed for the purposes of analysis of variance, and that it's better just doing by plotting. Plots like that, you look at that histogram and say that's close enough normal.
Okay.
This is a little bit more troublesome though, right?
That's
Not a very big sample. That's the smallest sample, but it's not bad, right? So, and that doesn't look too bad, but that one looks pretty normal, doesn't it?
Yeah, that looks very
Yeah. Okay. All right. So, okay. If you want, start on the next problem for homework, right? So you got 3 problems just like this, not just like this, but similar. I think one of them has 4 within the categories. It has 4 groups, right, instead of 3. And how are you guys doing at home? You fellas at home, when you don't comment, I assume you're either asleep, or like having dinner and drinking cocktails or something like that. I don't know what's going on. I have no way to judge what's happening. Okay, good. Thank you. All right, good. Let me know if you have any questions.
So this homework is
due next week?
Yeah, it's due next week, next Monday. And I'll post, a separate part which has just a numerical answer, so you can put that in and upload like A and B, like I did the others. So you can upload just the answers, so you'll know right away if you got the answer right. Okay. The first one already, but you'll know then, or at least those of you who were here for this or online for it will know already. But then you'll know for the others as well. You'll have some quick feedback on it. Okay, and again, remember now, in the coming weeks, we're going to be looking at different forms of data, right? Now we have a tool for dealing with categorical and numerical data where we have more than two groups. Categories represent, you have more than two groups within the category that you're looking for, the nominal data you're looking for. And next week, we might be looking at, well, what about if we have two sets of numerical data? Let's see. Okay, let's see if we can come up with some quick data. Okay, let's see. I'm going to open this file. And again, you're going to have to start looking at this as you start to plan what you want to do as a project. You're going to have to wrap your head around about what kind of data am I dealing with. Am I dealing with data that's just strictly categorical data? In other words, exposure. Yes, there's exposure. No, there's no exposure. Yes, there's a disease. No, there's no disease. Male, female. If you're looking at foodborne illnesses, did this person eat the salad at the church picnic, or did they not eat it? Did they get sick or not get sick, and so on and so forth. That's categorical data. We're going to use something called chi-square, something called odds ratio, relative risk. We're going to be looking at analysis that involves comparing categorical data. If we're looking at numerical data, we're going to look at something called regression and correlation. And I'll see if I can't come up with a quick example of that. And I think it should be open now. So I can get into the window here. Nope, not that one. Nope. For some reason it doesn't want to open. Oh, there. Is it down there? Still not opening. There we go. Okay. Let's see. Here's a variable unemployment rate, right, for all of these different states. I have unemployment rate, and we have, let's see, the murder rate. Let's see if there's an association between the unemployment rate and the murder rate. We've got a problem. We're used to dealing with categorical variable like means and analysis of variance. Now we have two lists of numbers. We have numerical variables, right? Well, one thing we can do to start off with is we can, as we really can do any times, we can look at it graphically. I'm going to look at it as a scatter dot. Scatter dot plot is just we're plotting one value against the other value on an XY coordinate. So for instance, for Alaska, the murder rate might be the y-axis and the unemployment rate might be the x-axis, and we were plotting the number 4.3 against 6.6. So murder rate is the y-axis, unemployment rate is the x-axis. I'm going to plot them, and there's the graph. Kind of hard to see, right? Okay. One of the reasons it's hard to see is we got, what's that guy there? An outlier, right? And it's, one of the things that outlier is doing is it's stretching, compressing the scale. right? In order to display that, it had to show all this empty space here. I'm going to get rid of that one. Okay, where is that one? That is, I think I know which one that's going to be. District of Columbia. Look at the violent crime district compared to all the others. I'm going to delete that one.
It's not on Gone Force?
What's that? No, it's not. That's next week. The session's over. It's 7:50. It's not quite. It's 7:50. You should be on your way. It's almost 7. And I was wrong. I thought it was 7:50 already. 7:45. You're supposed. I just wanted to show you that what we're going to be doing in the coming weeks, and that as you start to work on your projects or pick data sets out that you want to work on with your projects, keep in mind that the data set's going to govern what kind of tests you do with it. In other words, you can't squeeze everything into analysis of variance or into t-tests. You may have to use these other tests. Okay, but they're not going to be any harder to apply than analysis of variance. We have a great tool here, SPSS, which makes it really easy to apply these analyses to your data, right? And just as we're going to have tools, SPSS is also going to be a great tool for us to do correlation, regression, to figure out odds ratio for like that thing with the HIV and drug use and so on and so forth that I was describing, and so on. So I just wanted to just show you this graph now without that. I can see dialogue, scatter dot, okay, define. It's all in there. Let's see what it looks like this time. Up, that's a little easier to see now. Does it look like the murder rate goes up with unemployment? Kind of does, right? I mean, if I can actually get this to kind of maybe help me out and plot a little bit of a line that kind of balances the numbers that are above and below. Okay. And yeah, it looks kind of like, it's not a very good fit, but it looks kind of like there's an association there. Next week, when we talk about regression and correlation, we're going to really kind of analyze how good a relationship that is and see if we can quantify it and so on and so forth. Okay, how about, see if I can't find some, yes.
Would you recommend like any sources for finding data?
Oh, next week we're doing that. Levi, are we still having that thing next week with the Department of Health?
Yeah, so we're gonna have a guest speaker next week at 7 o'clock from the Department of Health, just to talk about all of the data available from the city. So she'll summarize like Epiquery, their data portal, and all of the different data that you can access from the city. So if you want to put off your decision on a project until then, you can.
And what they do, Department of Health surveys, I think they do it's a phone survey, isn't it? They survey thousands of people in New York City, asking them a variety of health questions, how much they exercise, how much, if they have diabetes, if they've ever been diagnosed with asthma, so on and so forth. So it's just like a treasure trove of data that's really easy to extract from that database. Also, we've started to post some on Blackboard. Did you get a chance to look at the